Really?
So I'm going to take it out on you all.
Excellent. We're here to listen.
When I went to work
Isn't
at
that what
Task,
you're for?
wall, and they were all
I
these
switched out of our
introverts.
department, yeah.
At about 10 o'clock, I go stand by the copy machine waiting for somebody to come out and make a copy so I could talk to somebody.
So you're that vulture, like, hangs out by the water cooler just waiting for the next victim?
When I was in the Army in basic training, of course you're not allowed to talk to anybody then, and I'd go about midnight, 1 o'clock in the morning, I'd go to the telephone booth and call the operator and talk to the operator. Back when there were operators. And we could do that.
So you weren't allowed to call home?
So ladies and gentlemen, we are live streaming. Just wanted to let you know. Control your language.
So we'll not say anything that will,
Watch your language.
But we also were wondering, like, this by streaming doesn't mean less people come. We have no idea.
We're about to find
I've
out.
noticed that with like meetings at work, like if you add a Skype invitation
just-
to it, like people in the office next to you will not go to the meeting. They'll just get away with calling.
So I just wanted to let you guys know you'll be seen if you stand this
About
close.
there, okay.
Right? You don't have to be seen, but if you want to be seen, then you'd have to be this close. And then you
Nobody
can check
will
where you
recognize
are
you.
on the right here at any given moment.
okay.
I move this one to the center?
No, that's the stream. I don't.
I know.
No, they're the same thing, man. There's also like a.
What are you trying to do, Ken?
This one is the delayed.
That one is delayed. That's right.
Okay.
So if you see
But
something
it's not-
inflammatory, run off to the computer as quickly as you can and press the delay.
No, it won't make a difference because if it's
If it captures it, it will
if
go
it
out.
captures it, it goes out.
Really?
Even if you stop it, yeah, it's done. I suppose we could put the delayed one for you guys here so that you can see yourself in 7 seconds.
That sounds confusing.
I
It all sounds
I used to
confusing.
work in radio and television.
Yeah.
You really don't have to worry about this. Just do your thing.
It was very disconcerting to hear yourself because you don't sound like you think you sound.
Or look as good as I can.
But it was very easy to double your audience. Because everybody be clapping, and you just tell everybody clap twice as fast, and you have twice the audience.
Twice the audience. That's right.
I thought you meant it was easy because there's only one person watching.
But right now we have 2 people watching, so that's more than the one.
There we go. We've already doubled the audience.
The double audience. That's
There
right.
you go. How to lie with statistics.
We got more time to log in.
Well, and I haven't announced it yet, so. You know.
Right.
Cool. Man, when
So I'm already
You're
standing up and
ready?
getting excited.
Oh, I should say that.
No,
Get
no,
excited.
that's why I say I can't sit anymore.
Sorry,
so
Joe,
I'm
we
going,
only know that
Oh,
there are people
okay.
my
watching
wife
in
will say,
parallel.
well, do you
There
know
might
what
be
you're
more
going
than one
to say?
person
When I tell her I
watching
have a
the
big
same
presentation.
Yeah.
No, because
I'm sorry,
there's
what?
nobody in
We
front
only
of
know
me
the
yet.
number
I
of
have to
people
see how
watching
they
in
react.
parallel. We don't know.
And then I'll
Yeah, it
talk
could be
to-
more than one person
Oh,
watching
okay.
the screen.
Normally
That's
that
right.
is-
They might have it up in a movie theatre
Board,
for a whole movie theatre full
Can
of
you-
people.
18
You know,
captains
what
in
kind of
general.
person would really put us up on a big screen like that? You.
Everybody has to
See
vote.
all our imperfections like
And the
that.
briefer, the slides go up, the briefer has to go through it. Sometimes one person hasn't yet voted. The briefer, they forgot to vote, and it became a standing routine. It says, well, I was waiting to hear the brief.
Yep, yep. Well, I've learned that when I go on vacation, if I take my movie camera, I can take pictures, but then I wasn't there. I mean, I don't participate,
yeah.
you don't
What you
participate
see
in the
through the
event, I
lens.
have to wait to watch it to see what we did.
I have photographic evidence that what you see through the camera is not true, because my wife watched me toss underhand a snowball into the camera
Ah,
and filmed it all the way.
well, I joke with you. Next year will be 45 years we've been married.
Wow. That's
Me
exciting.
too,
Yes.
72.
It's because she still thinks she's gonna fix me. I keep encouraging her.
You gotta leave enough hope.
Yeah, do you just make really small improvements every year?
Yes, right, that's right. Just a little bit, so she thinks there's hope. You can't ever dash that last little bit of hope.
Like, set expectations really low.
Yeah.
That's my do recording on it.
Looking back on it, I can see that because they say, you know, he would be perfect except for that, just that one little thing, but otherwise he's really good, so.
Disney now has a song for that.
Oh, yes?
He's a fixer-upper.
Ah. There's more truth to that than that.
Then Frozen.
I misspelled parallel.
Alright, it's been tweeted.
Be tweeted now, has it?
Yes.
We're still technologically advanced here. Let's make a start. We'll roll in, no doubt, late, fashionably late. Today we have the pleasure of having Emmet Beeker and Harvey to present some work on parallel computing and ADM. And what's interesting is Rob has been called over to LA to talk to people from DARPA and things on exactly this topic. So it's very, and for us, doing this stuff is very important. So I'm really looking forward to hearing more about it.
I guess
Oh,
you're
sure.
first.
Okay. I'll do the introduction because my section's up first. So Emmett and I are going to talk about parallel computing and agent-based modeling. So Emmett and I both work at MITRE, so it's a federally funded research development center. So we do nonprofit research for the government, which involves a lot of simulation. So Emmett currently works in the modeling and simulation department, and I just moved over and I work on our new high-performance computing cluster, also at MITRE. So I'm going to do a quick introduction to parallel computing. I don't know, how much experience does everyone have with parallel computing? From like a little to a lot. Okay. All right. That's a good spread. Emmett's going to talk about parallel simulation, discrete event simulations, and go through some example models, which probably, if you're doing research in that area, it's probably a good idea for starting points. And then I'm going to talk about something that I've been working on for the past 2 or 3 years, which is the massive scale agent-based modeling framework, which is a Python toolkit. So this is mostly for the people that have less experience with parallel computing. This is very, very heavily borrowed from this presentation by Blaise Barney at Lawrence Livermore National Laboratory. Lawrence Livermore is one of these big organizations that does tons and tons of parallel computing. And I was looking for ideas for this presentation, and somebody else had already done like an amazing tutorial. So I figured I'm not going to reinvent the wheel. So I really heavily borrowed everything from him. If you want to look at his tutorial, it's really good to walk through, and it gives like a full overview. It's really nice online. So I absolutely suggest looking at it. So starting out with serial computing, this is the traditional method. So you have discrete instructions. They're executed one after another. So you have, x equals 4, y equals 3, z equals x plus y, and then you have your instructions, and it's all done one after another for the code pieces. And it's all done on a single processor, so it can only be done in the order of things that happen. So you've got one processor, you go through step 1 through step n, and it just keeps going.
Are you going to point to things?
Maybe.
Maybe.
Yes, thank you. Okay.
Yeah, we'll have to wait till it says.
So up and down.
Oh, okay.
Hey.
That's different. Okay. All right. So parallel computing is just doing serial computing a bunch of different times. So you have simultaneous use of multiple resources. Probably all of your laptops now, they say it's a quad-core processor. You have an i7. It means that your computer can do way more than in the 90s when we all had, a lot worse computers. So you can divide your problem into discrete sections to be done concurrently. So each section breaks down further into a set of instructions. So in this one, you have multiple processors. They can all be doing the same set of instructions. They can all be doing the same instructions on different sets of data. There's a couple of different ways you can break out parallel computing. So here's an embarrassingly parallel problem. So let's say you want to compute the yearly batting statistics for all Major League Baseball players. So this is a lot of people. It's over 17,000 people, and you want to compute all their averages. The nice thing about baseball stats are they don't have anything to do with anybody else, right? Your batting average has nothing to do with, in some way it does have to do with somebody else's on your team batting average, but they're completely independent statistics when I compute, different players' batting averages. So you can do this all on one computer, and you can do them one at a time, so you can run through all the bats one at a time. You can compute their averages, but you can also split it out. So you can take the American League players and do them on one computer, and you can do the National League players on another computer, and then it should go roughly twice as fast, right? Oh, I'm gonna be doing that. But you can break it down even farther. So as many processes as you have, if you have a single computer for every single Major League Baseball player ever, it could go really fast. It probably wouldn't be the best use of your resources, but you could do things that way. There's also a little bit more complex thing, and this is more closely related to parallel simulation or distributed simulation, where you have things like a simple heat equation. So you have this equation, and so you have every one of these blocks needs to be computed. And then this is the, how do you point with this?
To a point.
Use your index finger.
No. So it's
Ah, right there. Okay. All right, so if you want to compute one of these little blocks, you have u of x and y. So to compute u of x and y, normally you need to compute everything around it. So that's how you do a heat equation. So all of these blocks are dependent on all the blocks around it. So you can do it on one computer, you can run through them one by one. You can also split it up onto multiple computers. The problem with this is this square is dependent on all the squares around it. So you run into issues and you run into the complications when you have to compute things. So this is all being done on my first computer, second computer, third, and fourth. They don't know what the other one's doing though. So you have to develop a system where you share all the information across multiple processors and you make sure that they know what the other one's doing. So that's when you get into, it's not embarrassingly parallel anymore. It goes from like moderately to extremely complicated when you want to do distributed computations. So when would you use parallel computing? So you really want to use this when you can break the problem into discrete pieces of work, when it's a problem that can be broken up. Not all problems can be broken up this way. Or if you want to break it up this way, it's going to be a lot harder than is really necessary. You should also really only do this when it's going to be solved faster with multiple resources than with a single resource. A lot of problems aren't really worth parallelizing. It's just going to be a waste of time and effort if you're trying to, you can spend a week parallelizing a program that's only going to take a week to run one time. Unless you're going to run it all the time, it's probably not worth the effort. There's a saying in parallel computing that premature optimization is the root of all evil. So you should never spend all this time optimizing something and then, like 2 months down the road realize that your code never did what it was supposed to do to begin with, but it runs really fast. So that is a big problem that I think everyone that has taken a parallel computing course realizes that they did their whole project and nothing actually works. And then computing resources, just because we're going to be talking about this a little bit. So a computing resource can be a single computer with multiple processors. So a lot of Dell computers, many computers now come with 8 cores or 4 to 8 cores. You can also have multiple components connected by network. So this is an example of that. So this is what a supercomputer really is. So you have a node. That's what you call like a compute. The terminology can be different. But you have a node, your node has memory, and your node has multiple cores. And they're all connected via network. And they share information over the network, and each of these cores can either have shared memory, or they can send information also over the network. So you use it to save time and money. So a lot of times you want something done overnight, and your program takes a week to run. You know, theoretically, you can run it on 8 cores, and it should finish 8 times as fast, and you don't have to wait a whole week for it to run. It doesn't always work out that way, but it can be cost effective. It can save you a lot of time and a lot of money. You also want to use it for larger, more complex problems. So if there's big data, if you want to run statistics on every baseball player of all time and you want to do it in 10 minutes, like the MLB website, if you want to download statistics and update them, they do it really fast. They're probably not running on, a single Dell laptop as their backend server for their computations. So big data, it makes a lot of sense to use parallel computing. Partial differential equations, if you want to solve a really big problem, if you want to do fluid flow and things like that, you want a big computer, and also for complex simulations. So if you want to have a very complex simulation, if you want to model all the people in the world, you cannot do that on a single laptop, on a single core. Sometimes you want to provide concurrency, and you want to effectively use underlying parallel hardware. Computers are now being made to support parallel tasks, and a lot of times they're faster at doing parallel tasks than they are if you really want to do something serially. So you can really, if you have GPUs and different types of hardware, you can really optimize yourself if you use those resources. So there's 3 commonly used parallel programming models that I'm just going to talk about because these are like the 3 big names that most people have heard about. So there's threads. Threads is OpenMP. So this is when you have shared memory programming. So threads break out and do small subtasks in parallel. So if I'm looping through every baseball player in the world, it's independent, so every core I have can do a different computation on a different player. As soon as they're done with that one, they move on to another player. You have distributed memory, which is MPI. This is another pretty well-known one for people that do parallel computing. You do tasks executed using their own local memory. So you exchange data using sending and receiving messages. MPI stands for the message passing interface. So you have machine A, they each do a task and then they share their data, then they go to the next task, they do task B, and then they share their data. So they're constantly communicating and sending information back and forth. Sending information back and forth is great, but it is also time consuming, so you have to realize that there's a big cost. You don't get perfect parallelization. If you have twice as many computers, you don't really get twice the speed up, especially if you have to send information between 2 computers. And then there's general purpose computing on GPUs. This is becoming a super hot topic right now, and everyone loves running their code on GPUs. You'll probably have a lot of times where you write code and someone will ask you if you can run it on GPUs, not knowing what it means, and you probably won't know what to say either. I don't really like when people ask me that, because then why would I do that? But it's something people like to talk about all the time. So GPUs are together when it's computationally intensive. So GPUs can't really do everything that CPUs can do, but there's more of them. You can put thousands on a chip or on a processor instead of, you know, the fewer ones that you can do for CPUs. So it's just a general overview of types of parallel computing. And now Emmett's going to talk about discrete event simulation.
How many people know what discrete event simulation is? If you all know, then I won't. A few don't. Okay. Good. Go down.
Oh, I do teach it.
Hey, so you better. Huh?
Only 1 week though.
Well, okay, we'll get there. So in 1775, simulation is deceiving by actions. So, and that's what we tried not to do too much of, I guess. When I say discrete, what I'm going to do is confuse you by telling you that I can be time-stepped or event-driven and be a discrete event simulation, except when I say discrete event simulation, I'm not going to mean time-stepped. So when I forget that I told you this, you remind me. There is not universal acceptance of what a discrete event simulation, whether time-stepped is in that category or not. Some would say yes and some would say no. And so the definition says yes, but I'm going to get confusing. And so when I do that, you say something and we'll straighten it out again. So the question is how to simulate a billiard ball. And one of the ways to do it is just to time step it through and see when something happens. Billiard ball hits the rail and we do something else. What if I have two balls? Well, I can do the same thing. I can time step it through and they'll overlap eventually and I'll know there's a collision. I'll process the collision and off they go. However, you can have problems with that sometimes. So, well, we'll go the other way first. The other thing I can do is I can predict when that ball will hit the wall or hit the rail. I can say it's going to do it in some amount of time, and nothing interesting is going to happen until then, so why bother time stepping when I can just move to that time and the ball hits the rail. It has another advantage in that when I was time stepping, I didn't know it hit the rail until the ball had actually passed through the railing a little bit, or the balls had overlapped. This way I can actually calculate the time exactly when it hits the rail. If I have more balls, I can do the same sort of thing. I can predict when the next event is by calculating when the balls will do something. That is, when will the ball hit a rail? So you have, that's what's on there. There'll be some amount of time. I also have to calculate when the balls might hit each other. So it starts getting more complicated. And when I watch what happens, I go to the next event. Notice that, let me back up. So I've calculated what the next event is, and what's going to happen is that purple ball will hit the rail. So I move to that time, but these balls haven't moved. And that's because these balls were not involved in that event. So as far as those balls are concerned, they figured out the next thing that's going to happen for them, and it had nothing to do with this, so I haven't worried about them, I've just disregarded them. So if I watch my simulation taking place, visualizing what's happening, this is what I would see. I've processed the purple ball, and I say, what's the next event that's going to happen? Which is those two balls colliding. And notice the purple ball doesn't move, because he hasn't done anything yet. His next event is when he's going to hit this rail. And so on. And so I progress through the simulation from interesting event to interesting event and skip over that stuff in the middle. And we can continue on and on. So now the question is, which is better? Better meaning more efficient to do. And the answer is it depends. It's the answer to all important questions, right? Because what happens is if I keep adding balls to that table, I have a lot more calculations to do to figure out when the balls are going to collide. I have to calculate every pair of balls to see when that pair might collide, and with the rails. So it starts getting a lot of calculations, and eventually the number of calculations I need to predict the next event takes more time than just stepping through to see what happens. And so if you have a problem and you want to turn it into a discrete event simulation, you need to look at the problem and say, does it lend itself to that, Or am I better off just doing what I would normally do, and that's step through? And the answer again is, you know what, it depends on my model, and may in fact depend on some of the parameters in my model, which is actually more efficient. So in the 70s, we solved that problem and said, let's go on to something else. An example of where we encountered this, we were using Repast Symphony to do a large-scale model, had 100,000 agents or so in it, and what happened is every time step, every tick, every agent would test to see if he would do something. That's all they did. It was just one thing that each of those agents might do with some probability, say 20%. Now Repast has a queue. You can schedule your events on the queue, so I can schedule myself every tick to have an event. And what that basically does is, when it's my turn, I draw a number between 1 and 0, and I say, is it less than 0.2? If so, I'll do this event. Otherwise, I just schedule myself for the next event, for the next time period. And we go on. So that's one way to do it, and it turns out that there might be better ways, more efficient ways, I won't say better. So the normal way was this. Oh, and by the way, when Repast does that, what it really does is on its time queue, it looks at the next time step, what's the time of the next event, finds all of the events with that time, moves it to another queue, which is why it's hard to schedule another event for the same time in Repast. Can be done, but you have to be careful in how you do it. And then might pick randomly from that queue if you want to randomize the events during the time step. So what we looked at was, well, what about if we predict when this event will happen? So instead of drawing from the norm or from the uniform distribution, I draw from the geometric distribution, which says, when I flip my coin, how long do I have to flip it till I get a heads? Instead of saying, I'm going to flip it, is it heads or tails? I say, how many ticks, how many flips will it be before I get a head, and schedule my event for that time. And so that was the second thing we tried. And the third thing we said, you know, all these agents are doing exactly the same thing. Let's just put one event on the queue. And at that event, I'll go through my array of agents, my list of agents, and each one will do a draw. Should I poll and see what people think will be best, most efficient? Okay. So the top line is the normal Repast way. I schedule on my regular queue, all the agents do a draw, and at some probability, and so probabilities are along the bottom. So a 20% probability, which was the example I have, would be about here. What's interesting is that this is the normal. The yellow line is the geometric pick, which says if I have 0 chance, no events get put on the queue, right? It'll never happen. If I have 100% chance, way out there, then I'm doing the same thing, essentially, except I'm doing a lot more calculations to figure out when to schedule. It is harder to do a geometric distribution than a uniform. So and what's interesting is that the crossing is out there at about 85%. That if my percentage of doing an action is less than 85%, I'm actually more efficient to predict when it happens instead of flipping to see if it happens now, or doing that draw from the uniform. But looky here, if I don't use the queue at all, if I just go through my list of agents, that was fastest of all, unless my probability is low. If I have a low probability, then I'm still better off doing the geometric. Which says, when you have a good idea, you ought to go test it, because you never know what might be right. That's the nice thing about working at a federally funded research and development center, is they give you time to do research, and you don't have to just produce. Okay, so let's talk about then parallelizing some of these things when you have lots of agents. Embarrassingly parallel, they're great things to work on. I love it when somebody comes to me with a problem and they say, hey, I need this. I have 100 million things, and it turns out they're all independent. Can you put them in parallel? And I said, well, sure. In fact, we had a problem where we were doing a financial simulation of the financial markets, and the person in charge says, I want you to run lots and lots of runs because I want to find when the market has this pattern in our simulation, I want to find some examples of that. And I said, well, I came back the next day and says, I've run 100,000 of them, and I still haven't found it. Says, well, I know if you run enough, you'll do it. Go back and run some more. It took about 10 hours a run. So we got as many computers as we could, ran them over the weekend, came back and said, okay, I have run 10 million of them now, and I found 3. Actually, running them was one thing. I have to now look at all the data to find a pattern of a week out of this 180 days that matched the pattern that he wanted. That was the harder part. And so the question is, if I'm going to run 10 million runs, do I really want to run them in parallel? The answer is no. You know, if I have a million computers and I'm going to do 10 million runs, I ought to run 10 runs on each of the computers. Right? Don't parallelize it because there's overhead in the parallelization. Even if it's a little tiny bit, there's overhead and it'll take you longer. So if I'm going to do lots of runs, maybe I don't even want to think about parallelizing the problem. And the other side of that is the real problem was analyzing the data. And what we did was, after we ran that problem, we looked at that data on that machine to see if it matched, and if it didn't, we threw it away, because who wants to keep all that data around, right? Highly interactive. This is the example that Christine gave, where what if what I want to do on one part of the model, one agent, depends on what other agents are doing. What do I do then? For example, I'm doing a network simulation, and it really depends on things happening elsewhere. And the answer is, you really need to study those problems to say, is there some way of organizing them to put the things that interact on the same computer so I can share less information? And when I have to share information, it always takes time and there's always overhead. And then we have this synchronizing discrete event simulations. What you have to do in a discrete event simulation is predict the next event, right? So I want to execute the next event. Well, what if my events are all spread out on different nodes and different computers? How do I know whether I can process this event on this computer or not without finding out if it's the next event? And we'll get to that one in a minute. The key here is I want to be able to do events on multiple computers. And the question is, when can I do that? Okay, so, let's see. I'm going to show a couple examples of parallel discrete event simulations. Some of the things you want to look at is, how do I limit the data I have to send and the synchronization I have to do? And so part of that is, well, I don't send all the state every time. I'll give you the initial state and I only tell you when something changes. It makes it easy. Sometimes I'll say I'll only send stuff that you need. Now that's a problem because the guy sending it often doesn't know what you need. The guy on the other end knows what he needs, but you're sending it and you know which part of that he wants to know about. And so that can be an issue, and so now I need a way of telling the other guy what to send me. And maybe I don't need to send all of the state to everybody. Maybe I can arrange it in such a way that I only have to send state to a couple nodes and speed up the communications. Nobody's glazed over yet, quite. Okay, so say I have four computers, 4 timelines, 4 event queues with the next event on each one, and those are times. And I say, okay, when's the next event? When's the earliest event? And that's this one. So we'll start it at time 10.0. Now the question is, when can I execute these events on the computer? Well, I could share information across all the computers and say, who has the next event? And so, this guy, okay. And who has the next one? This guy. Who has the next one? This guy. And who has the next one? Oh, I find, this one, and then I have a tie. And maybe the ties can be executed at the same time, or maybe they can't. But that's a problem you have regardless of whether they're in parallel or not. What do you do with events at the same time? But that doesn't speed anything up. In fact, it slows it down because I have to tell everybody when my time is for my next event. And you say, you got it, you go. What I really want to know is, when can I do this event? And the answer is, I can do it when none of the events that the other guys are going to do will affect the results of this event. So that's what I have to be able to tell. I have to know that that event is independent of this event, and I can process them at the same time. And so all about what parallel discrete event simulation is all about is determining that independence. When can I do those things? Give you a simple example. I have 3 airports, and what I'm simulating is what happens at the airport. I don't care about the flying time. So once an airplane departs, he's going to arrive, I'm going to service him, turn him around, passenger's going to get on, he's going to depart and go to some other airport. So I don't really care about what happens. So it takes 4 hours to fly either from A to C or C to A. We'll pretend like there's no such thing as wind. 3 hours, 2 hours. And so when I start, I have an airplane that starts the simulation, and I say, he's leaving. So from A to C, he departs at time 0. And the airport plane from port B, airport B will start at 1.5. Then airport C, over here, knows what time the first airplane is going to get there. Right? So if I always tell everybody else when the next airplane is going to them, I release them in order, then airport C always can tell when the airplanes will be arriving from the other airports. And so until that airplane gets here, I can do anything I want locally. The airport can be simulated up till the time that airplane arrives, and then I have to worry about it. So if I keep telling the other airports what time the airplane departs, then I get a buffer. In this case, the minimum buffer is 2 hours. I can be really clever and use the one between the airports, or what we normally do is we just use the minimum one, and we say the minimum look ahead is 2 hours. I get 2 hours advance notice of anything happening here that's going to cause me to do something else. So I can process any events for 2 hours past the time the airplane leaves here, or 4 hours from here, or if I'm lazy, 2 hours from anywhere. Right? And so that tells me that I can process these events, and I have to wait to hear from him for something else. That's conservative. I won't go ahead. I'll wait till I get a message. There's also optimistic simulation. And basically what it says, I'll go ahead and I'll process everything I know about. I'll just keep working. And when you tell me that an airplane left here to go to there, and if I'm past that 2 hour time, I'll back up. I'll go back to that time, reset my clock. Oh, and I might have told this guy I was sending an airplane to him. So now I have to send him a message that says, you know that event I told you about? I didn't do it really. Take it back and I'll tell you again. And so I back up. And for 15 years, there were wars in the simulation community about whether this was more efficient or less efficient than conservative time management. And it turns out the answer is it depends. So we'll leave it at that. There is, in fact, a paper that said if I do this, optimistic, it actually runs faster than if I do it serially. Well, how can that be? You know, if I use 2 computers, how can it be more than twice as fast? And the answer was the problems were large on a single computer, but when I put them on multiple computers, the data I needed all stayed in the cache. And so I didn't access main memory, and so it actually sped the problem up because I needed less memory. So it had nothing to do with the problem at all. Okay, quickly. Sponsor said, hey, I've got this model that I'm using now, this simulation, use Mana, which is, I'll show you a picture of it in a minute, produced by the New Zealand MOD, Ministry of Defense. And they said, it covers my 50 kilometers. What I'd really like to do is make it cover the whole border of Arizona. Can you do that? No, by the way, I have certified, this model is certified by Johns Hopkins University to be accurate and do what we're supposed to do. And so you can't change the model, or we have to recertify it. So figure out some way of doing this. So there's what the model looks like, the simulation. These are little people. And the red people run across the border and they try to go to those flags up there, and there's rules that say stay away from the blue guys, and the blue guys' rules are catch as many red guys as you can, essentially. What you're allowed to know, the blue guys can have communication so they can tell each other what they see, the red guys don't. Okay, so there's 50 kilometers, and so the simple solution is to just put them side by side. And now we run into the problem that Christine was talking about is, okay, if how I behave depends on stuff around me, what do I do along these borders? And so the solution was that we'll overlap the borders. What I'll do is I'll stick them side by side, and then I'll stick another one down over the top of it. And so in this simulation, in one of the simulations, this simulation will control the guys in the middle, all this 50%. And the 25% on the edges, I'll lay another mana over it so that every mana is controlling the guys in the middle. So that if I'm here, there, well, we got an animation, a little smiley face to show. So what happens is the right guy's controlling it until he gets, so, and when he gets to the edge of this one, this mana creates a ghost image, and the status from this model goes to this model, and I don't have to send it to anybody else. I only have to send it to the one guy, which helps a lot. Then when he gets to the next border there, control gets transferred, and now he becomes the ghost, and he becomes the controller. And then that keeps going. As I go across, we transfer back, and we create the ghost in the other one. There we go. And finally do it. And so what we end up with is a set of manas, and then we run it in parallel. Interesting things happened. We were running them on a number of machines that were quad processor machines. What that really means is you had 2 real processors and 2 virtual, but they're stealing cycles from each other. So you really had 2 processors per machine. And what happens is you have the mana processing. There is some amount of time for overhead to do that communications. And then everybody except the slowest guy, that usually has the most agents in it, takes longer to process. These guys just are waiting for him to get done so they know what to do. And so they're sitting there waiting. One of the things you will try to do when you do your parallel discrete event simulation is try to even the loads so they all do about the same amount of work. If you have one guy that's doing 98% of the work and 100 nodes that are doing that little tiny bit, it does you no good at all. And that's kind of what we found. And the question was, well, when I go from out there for that 19 federates, how come the time goes up so much? And they said, it's obviously overhead. It takes more overhead when I have 19 federates. But it turned out that wasn't the answer. The answer was, no, some node, and it's a different node on different times, but the worst node is the guy that's going to control the time each time. And so what happened is when we had down to around 11 nodes, the loads were balanced more or less. But when I got to 19, there was always this one node that had something peculiar in it that caused it to run longer, and that's why the time went up. Questions on that one for? Yeah.
I have a question. So you have a controller, right, that controls, and then they hand the control of the ghost over.
Yes.
Is there a point where you have to deconflict the different ghosts when it switches over? I mean, are these manas running in parallel?
Yes.
At some point?
So each one is running on its own computer, and its own space. Each one has their own memory. And what happens is during this what we call DLL time, what happens is my mana is sending a communication to that mana. I know which he is because I know the position of my mana, the agents that are running around. Mm-hmm. And so there's only one other computer that cares, right? Because they've made, they don't overlap except the ones that do. And so I know his coordinates because they're fixed coordinates and they're integers. He's got to be in one or the other. So there's only one ghost at any time. So unless I'm on the outside edge,
so you have the real, and then you have the ghost.
You have a ghost in some other mana. unless I'm on the outside edge. The outside edge of the last monas don't have any. And that's another thing you have to worry about is edge conditions. It makes it real simple until you get the guy on the edge. And then who does he send to? Right? So there's a difference. Yes?
On that same topic, do you care about the history of the agent?
No. And this, well, we did. We actually print out a log from each one. And the guy that's controlling it, his log counts. And he's only controlling, you know, so everybody's controlled by somebody. So there is a log for where he is. And after you're all done, you take and consolidate. And you can, so you have to name the agents. And what we did was, the first agent was the, you know, where he started, what mana he started in, and then which mana he was, which agent he was in that mana. Because he might move across to other manas during the time, but his name doesn't change. So, but that's a good point, is that when you get done, you may have to do something about consolidating all that data and putting it together and figuring out what it means. A little bit bigger. We did a influenza study on the questions were, said, hey, you know, there might be a pandemic and we might have to do things like tell everybody to telecommute and stay at home. If that happens, will the networks support the ongoing trading, essentially the economy, which to them meant, can traders trade for their stocks? Can I buy and sell stocks? Will the internet support that? You have to remember that this study was done in 2005 now, before fiber. Right? So he said, okay, and when we do it, we want you to use a large area to simulate. We want you to use either New York or Chicago. And you know which we picked, right? Chicago. Right? Because there's 20 million people in New York and there's only 10 million people in Chicago. So we got a 50% chance better of succeeding if we use Chicago. Okay. So there were actually two models. I'm only going to talk about the epidemiology model and look at what people normally do, what they do under quarantine, and we might add vaccination. We did, but we didn't. They didn't ask for that. SEIR, people start off susceptible. If you come in contact with somebody who is infectious, then you can catch the disease with some probability based on how long you're there, and then you become exposed. Exposed means you're in that incubation period, you don't have any symptoms and you're not contagious. Eventually, after some amount of time, you become infectious. You are now contagious and you have symptoms. Probably you're at work when that happens, or if you're a student, you're at school. You may try to tough it out for the day, in which case you're making other people sick. From there, you either recover or perhaps die, depending on the severity of this disease. It doesn't really matter because once you recover or die, you are no longer susceptible to be getting the disease again. So the first thing that epidemiologists do is they use the ordinary differential equation model that says, at any given time step, I have some number of people that are going to catch the disease. That's beta. It's a percentage based on the number of susceptibles and the number of infectious people that are together, right? And so that's the curve, except that assumes everybody's in one big room, and this is what would happen if we all stayed in that room until the disease was over. So they came, Mr. Levy came to us and said, I have this net logo model, I have 800 agents in it, and what I do is each time I take a guy out, he dies, I put one new guy in, he's born, and then I do this other stuff, just like I said before. And I simulate 180 days, and it takes 3.5 hours. Can you use that to do my 10 million people I need to do for Chicago? And the answer is, well, not in NetLogo, because right? NetLogo won't take 10 million people, first of all. In fact, when we calculated it out, we figured that if we could do it, it would take 180 years to do that simulation. So probably we don't have time. So we abandoned that logo. We'll use C to write it in, because in C I can manipulate almost to machine level if I need to. I have lots of options for the queue. I just throw them up there so someday when you look at it, you can see what they are and you can investigate them if you care. But they make a difference. And the answer again is, which should I use? And it depends on your problem. And we wanted to execute in parallel. And we went from a time step to a discrete event simulation because the probability of catching the disease inside of 5 minutes is very low. So instead of going 5 minutes at a time for 10 million people, I said, let's calculate how long it will be when those two come in contact, and that's what we'll do. So describing probability distribution, it says this is the probability that I'll get a 1 for a 50% coin flip from the geometric distribution. I have a 50% probability. That makes sense. If I flip a coin, 50% of the time I should get a heads on the first try. If I don't get a head, a quarter of the time I'll get it with 2 tries, an eighth of the time, a 16th of the time. So what that gives me is a number that says, for you, this is how many times you had to flip the coin in order to get that. And another great thing about the geometric distribution is it's memoryless. So let's say that I predicted that he's going to get the disease, he's going to be exposed in 10 ticks. And something changes at 5 ticks. I can do another draw at 5 ticks, and I get the same distribution for the rest of the time as I had before if I hadn't done the redraw. Now that's going to confuse you, and I had to actually write a small program and generate data before I believed it, even though the textbooks all agreed. So I encourage you to do that. So what we had was cells, and the events were somebody moved into the cell, somebody moved out of the cell, somebody became infectious, and somebody became, well, it doesn't matter if I become exposed, right? Because that's not going to change, well, it does matter, I guess. It doesn't change too much. So those are the things. I change state of an agent. I move from one place to another. We use census data for Chicago, and the Department of Transportation actually has carpooling and how many people ride bicycles and where they're going to. And so we had a typical Chicago, right? I can't tell individuals, but I know by track who's going to where and what they're doing. And it turned out that we really didn't have to worry about transportation. That just gave us more detail that didn't change the model. Lots of things. So found out these are the number of people that become exposed or become infectious on a given day. R is the number of people on average that an infectious person has made exposed. Okay, right? So for a disease to progress, every infectious person has to make at least one other guy be exposed. In fact, it turns out that it needs to be around 1.3 for a disease to spread. If it's less than 1.3, here it dies out. Notice that out of my 10 million people, on the worst day, 9 people got sick. And then it died out. Changing transmissivity, well, changing the latency a little bit caused the epidemic. And so it shows that, and when I calculate the R, the average R, it's about 1.5. And so the difference between a flu dying out and a flu causing a pandemic can be very small. And that's what we had. Questions? Speak too quickly. Not quickly enough. I didn't give you a whole lot.
So this is kind of, so there's a bunch of different ways to write agent-based models, especially distributed, and I'll go into that a little bit. This is something I've been working on for the past couple years with James Gentile, who went to Notre Dame. Massive scale agent-based modeling module in Python. It's just a Python module you can import and you can run parallel simulations. It's not available yet. I'm working on it. It's going to be on GitHub soon. I have to go through our work public release process, which means like sending people that don't care about my code a lot of emails asking them to check a box. So working on it. So some of this is stuff Emmet and I have already gone over. So, why do you need massive scale agent-based models? So you want to model, hundreds of millions of agents. The software I have right now, I've been able to test it on up to 500 million agents you can model and simulate. And you need distributed computing. This is kind of how it all lays out. So you have a root process. So one of the way that my software works is you have a root process that controls the time steps. It makes it a little bit easier than all the processors checking with each other, like, hey, what time step are you on? You ask everybody sends it back. A root processor is kind of like the brain of the distributed simulation. That one keeps track of this root process individually asks everyone where they're at. He finds out where they're all at. He finds that lowest time step, and he does a minimum function on an array of time steps he gets in. And a control. So processor 5 has agents, processor 1 has agents. Also the root processor can or cannot have their own agents. Normally you do, just because finding the minimum of a function isn't that hard, or finding the minimum of 5 numbers isn't that difficult. So they can normally also handle agents. So these are tools that you're probably somewhat familiar with. NetLogo is pretty common, really easy to prototype in. We use it a lot. It's like one of the easiest ways to get started. You can see how everything looks. You can make things look pretty. Then there's Mason, which I've done a lot of modeling in. I like it. It's way less dependent on visualization than Repast is. I think Repast is a little too viz heavy. Mason works well. Repast Symphony works well. And then there's Repast for high performance computing. So this one is actually distributed, but it's written in C++, so it's not great for everyone. Not everyone that wants to write code and build models really wants to write in C++. A lot of people don't. There's
a D-Mason?
D-Mason?
Yeah.
I know there's Mason. I haven't
No,
had an-
D-Mason.
What is D-Mason?
Distributed.
Oh, really? When did that come out?
I don't know if it's
Okay.
out, unquote, but
Okay.
Is that online?
it's developed in Italy.
Oh, okay.
And it's being used, and I
I'll
think there's
check
links
that
to it
out.
from the Mason
From
website.
the Mason? Okay. I'll have to look into that. That's exciting. So this is kind of, when I put the slide together, this was what I could find for distributed agent-based models. And so what I did with James Gentile is we built a tool that's a Python module. And Python's really good to use. I don't know how many people in here have Python experience. It's really good for rapid prototyping. It's not as easy as NetLogo, but it's really simple. It's like MATLAB. You can kind of basically write out your thoughts. It looks like pseudocode to people that write in C. It's pretty quick, and Python also has the message passing interface, which I talked about earlier, which allows you to send messages between multiple processors. The people that work on this Python module just basically put a giant wrapper around some C code. So we have a completed module. You can run simulations with over 500 million agents. We have a couple of different ways to do agent synchronization. Like Emmett said, this is kind of a hard technique when you're doing. And the best part of this is that it's abstracted from the user. So when the user goes to build their model and write their code, you don't actually have to do the part where you distribute the agents. You just say how many processes you want to work on, and it does it for you. So here's how the module works. So you have an element, and an element is an agent. So this can be a taxpayer, it can be a wolf or a sheep, it can be a person that could have a disease. You have an element form. So this is a ghost element. This is kind of what Emmett talked about before. It's pretty common in parallel computing to have, just ghosts on different processors. You have an element ID. Everybody has a unique identifier. You have an element ID generator. You have a directory. And then there's a scheduler. The scheduler kind of controls what everyone's doing. Okay, there's containers, and then there's the overall model. So here's an example. So if you want, are you guys familiar with one of the most common agent-based models is you do this human and zombie one, which is kind of, when you're infected, you just become a zombie, and you never recover because you're a zombie. So you have 2 types of agents. You have humans and zombies. So every zombie has a state, and then they have neighbors. So they have people that they can potentially infect. Humans also have a state, and they have neighbors. And then you have this ghost. So you have a ghost form as a zombie. That's kind of just like a placeholder on a different processor. Same thing for humans. You have a list of humans, you have a list of all the zombies. That's just kind of how this would work out.
Christian,
Yeah.
I'm sorry, can we go back to and this is probably really basic.
Sure.
The element is the class?
Yeah, so the element is just an overlying class. So
Okay.
an agent is a type of element, and zombies and humans.
So why is the the zombie here is the different, would those be the different states of the agents, like ghosts, and why are there ghost agents in parallel computing?
I think.
Why do we
Can I-
create ghost agents?
The ghost agent holds the state of an agent that's actually being processed on a different node.
Oh.
So that's why it's called a ghost. If I want to know about him, I don't want to ask that other computer. What I want to do is, I'm going to anticipate which computers need to know about that person, that one, and send you the data during that inner space so that you keep it in a ghost. And so as an agent, when I want to know what the status is, or the data is, I don't have to ask the computer, I can look at the ghost agent.
So technically, every processor or every thread knows, theoretically speaking, about the whole simulation,
No.
but it only processes a portion of it.
Yes and no. The key is to only send you the stuff that you're going to need to know about. I don't want to send you the state of everything. I know which of those agents you want to look at. I'll create ghosts for them in you,
So-
and I will keep them updated.
So in your model, you said there was like a central scheduler.
Yeah.
Is that the only, so each individual processor doesn't know about the ghosts, that central one knows about the ghosts?
So let me go through this,
Yeah,
and
no,
I probably
I'm
should have
confused,
had
I'm
these
sorry.
first. No, because I think this will explain it, and if it doesn't, let me know. So you have agents that make decisions based on the states of their neighbors, right? You care about what your neighbors do. So a lot of models, you'll go and you'll ask all your neighbors, like, hey, have you heard this rumor? If enough have heard the rumor, then you also hear the rumor. So with, all these are different processors. So the blue, green, let's say we have 3 processors here. So, it's all outlined like that. So processor 1 doesn't need to know what, this guy is doing. He does need to know this neighbor, though. He has a ghost copy for this neighbor. He only needs to know, the buddies of his own agents. And that's the one that he has ghost copies of. So processor 1 is going to have a ghost copy for this one, and for this little green guy, they have to be aware of those. So here's how information sharing works. So maybe this might help a little bit. So this explains the ghost. So you have processor 1 and processor 2. So in this example, the root node thing doesn't really matter. It's just kind of a central node. Normally it's going to be whatever processor 1. So you have A1, A2, A3, you have B1, B2, B3, and then the arrows show who I care about. So you can see that A2 cares about what B1 does. B1 doesn't care about A2 though. They don't have to be mutual relationships. So what happens here is they make ghost copies. So because A1 cares about B2, A2 cares about B1, he's going to make a ghost copy. A3 was interested in B3, and then you can see that B3 and A3, they had a mutual relationship. So there's going to be 2 ghost copies. So that's how the ghost copies work. So nobody cares about A1 besides processor 1. So processor 2 doesn't have a ghost of that one.
But if there's movement, A1 would therefore want to know.
It might.
It
Yeah.
might, yeah.
Then you would.
Yeah.
And is there more burden involved then when you have to create these ghosts?
Yeah.
Complicated, yeah.
Because so potentially, like, if you look at that, like, processor 1 originally has to deal with 3 agents.
Okay.
And now it's got to deal with 5 agents.
Yeah.
Right. So is it more efficient then for one processor to look after 5 agents and 2 processors looking after 6?
It
If it
depends.
can
So
jump
in this
across.
simulation, like this
Yeah, it's
example,
wrong.
absolutely not. Like you,
Right.
yeah, no. I mean, if you're only doing 5 things, you should absolutely just do it on one computer.
Yeah.
It depends on the interconnectedness of the network. So if I have a very highly interconnected network, and everyone needs information from everyone else, it probably doesn't make sense to share that much information.
Right.
It's going to bog down the network. But if I have a loosely connected network, it's going to be way better to just make copies of the agents. Then I've done work before, I don't think it's in this presentation, where you can kind of see how much slower it gets with the interconnectedness of the network. So, 10% of your neighbors are on another node, it's not that bad. If 90% of your neighbors are on another node, it's just silly to do it this way. Yes.
It's a lot easier to put 3 on a slide than it is.
Yeah.
Put a
I
thousand.
know.
Yeah. No, you're absolutely right, it's good insight.
Yeah.
And which is why you want to be careful allowing the controller to put your agents on there at random,
Mhm.
right?
Yeah, and
Because there
also,
is some better way to do it.
yeah, and so one of the things I'm building into is being able to group them. So if you've got, a ton of agents, there's going to be a best way to group them into 5 or 6 groups, and you can do things based on that. Some sort of algorithm you can make sure your agents are well sorted out.
Some people, in fact, run the simulation for a little bit of time to see who interacts, and then go back and move them to distribute them
So-
according to what happens.
Just a question, when you're developing your system, when the guys at D. Mason came over here, when they were testing their simulation,
Uh-huh.
they were using flockers
Okay.
as their example, right? Because
Okay.
it easily scales up.
Yeah.
But then I asked them, I'm like, great, flockers is great, but it's very abstract. And I
Yeah.
gave them a real world model,
Yeah.
and that broke their system.
Okay.
Now, that might happen here as well, if it's, right? If you had like real, when I say real world, like real spatial data network.
Yeah.
How robust is yours? I know you haven't finished it yet.
So I work on this by myself, so it's moderately, it's not robust. But there's things that come up, so I build it as it comes up. So there's some things that, so you know Matt Kohler, he works at MITRE with us, and he does a lot of simulation, and he comes to me all the time. He's like, Christine, do this in MABM, and I'm like, no, I don't think so. But you have to think about it, and you have to figure out new ways to do it.
You have to remember that Matt's a lawyer.
Yeah. So I'm working on more example models, and they're so it's in progress. So I'm going to open source it soon and put it online, and hopefully, if anybody else wants to, figure out ways to program their stuff, and it's not just me doing all the thinking. But I'm adding different types of models as I go along. So I've got I have a rumor model, and I have a taxpayer compliance model, and we just did one for started working on one for census data in Spain and trying to determine how people move, the Schelling model in Spain, and trying to I kind of add features as I realize that I need them for the model. So it's under development. Probably similar to the
exactly same as MITRE.
Yeah.
It's constantly being developed like that.
Yeah. So it's robust-ish. It depends on what you're trying to do. So, all right. So you have your ghost copies. That's how that works out. So if you want to update your agents, so this is the exact same layout as before. So you update agents on their own processor at every time step. So processor 1 and processor 2, they can operate completely independently because they've got these ghost copies. So they don't have to share information during a time step because we know what B1 is and we know what B3 are at the last time step. So we go through, we look at all of our agents, and then they have their states and they share information. So processor 2, this is something that you set up at the beginning. Yeah.
If the communication failed, do you have a way to check if the information was updated or not in the processing?
If the communication fails, the program will stop. It'll get stuck. It's built into...
Really good point, because when you get to huge problems, you can almost guarantee that sometime one of those computers is going to fail.
Yeah.
And so when you do that on real high-performance assets, you need to program in fault tolerance, how to catch up in what you're going to do when that happens.
Yeah. So
That's something you have to think of.
Yeah, right now there's not a ton of it built in, but the way it works is, so the root processor is just waiting to hear, and if he doesn't hear from one of the other nodes, he's just not going to do anything. You just won't proceed. The simulation will just stop, and you can either, if you're keeping log files, you'll realize that it's not going, or if you're not keeping log files, you'll just wait a week, and then you'll realize that nothing happened, and it stopped on step 1. So it's, that part's a little bit on the developer, but it won't keep going if it's not getting the information. So, all right, so what processor 1 and processor 2 do, they know it ahead of time, so at the beginning of the simulation, you set up what each processor needs from the other nodes. So processor 2 knows that processor 1 cares about B1 and B3, and processor 1 knows that processor 2 cares about A2 and A3. They're going to send this information, and then they're going to update their ghost agents. So we have 2 synchronization techniques. So that's just how the updating goes. You just share the information at the end of every time step. But it can be really slow, right? If you have a bunch of ghost copies and you have a bunch of interactions, it's going to take a really long time to send all information every single time between nodes. So something Emmet talked about earlier is we just send pertinent information. You just send pertinent information that has changed. So if, B3 is never changing, why would you waste all that time sending information on B3 if nothing's happened? So we have a technique called agent watches, and that is event-driven information being sent. So this shows requests versus watches. Watches is when every single time something happens, you send all the information every single time. Watches just means that you send only the pertinent information. So same diagram as before. So here, the top and the bottom are the same. The communication techniques are different. So A1 has changed and B3 has changed. So just remember, A1, nobody cares about A1. B3 we do care about though. So what happens is in watches, it sends all the information anyway. So it still sends all the information on B1, B3, sends all the information on A2, A3, even though it didn't change. What happens when you do watches? You only send information about B3. And you can see, if you want to scale this up to a couple 100 million agents on each processor, sending a quarter of the information is going to be a lot faster than sending 100% of the information. And it just continues on like that. So now we have A2 is updated in B2. You keep sending all the information with requests. With watches, you're really only sending the pertinent information.
So what is the advantage of using agent request over agent watch? I mean, you just seem to be
There really
processing
isn't one.
for...
It's way easier to program.
Okay.
That's the main advantage.
A little library that makes it really easy.
Yeah.
You'll put that in there, right?
Yeah. Oh no. So for the user, it doesn't make a difference. for me, when I was programming it, request was a lot easier to code, and then
So
watch
that's
is
the first one you did.
yeah. So request was like, this is how it works, and then trying to make it faster was like the nightmare. So yes.
Have you used it for testing speed of processing or checking for errors or something?
Yeah, we ran a couple of different experiments trying to run it, on, so if I run this on one processor, do I get the exact same results? If I run it on 4 processors, if I use request versus watches, do I get the exact same thing for a couple of different models? So I've gone through all that. Yeah. And it works, I think, so, as far as I can tell. Yeah.
This issue with the node going down,
Yeah.
it seems like before you make the first step, you have some distribution step where
Yeah.
you decide where the agents are and where the ghosts are.
Yeah.
It seems like in the root node, you would just say that if there was a timeout, if you didn't hear anything, you would just do a redistribute step on all of the ones that are responding.
That's true.
And then it wouldn't be.
Well, there's things you can do, and the issue there is, if I take time to send back a message that says, I received your data, now you've increased the processing time, and because it is so reliable these days, what we say is, we'll just assume you got it. And so you actually, like you say, you should test for it every once in a while to figure out why I'm sitting still. But that's, you're absolutely right. Now, it's different between TCP and UDP, for example.
Yeah.
For anybody that knows that, no, never mind, wrong audience.
It's one direction versus
Right,
bi-direction.
whether I want to acknowledge or not, or if I just send it and assume you got it.
Yeah, something like that should absolutely be built in for like redundancy, making sure that you can redistribute it. Right now, if one of the nodes goes down, you just have to start over again.
And again, for the size of projects that we normally use, where you can see all your computers, that's not a big deal. If you're doing it in a lab where they have thousands and thousands of computers, it's a big deal.
Yeah. No, so far I've pretty much kept it to, I think I've only scaled it to like 64 processors for pretty short simulations, so I haven't had any major fails. But that's, again, just me working
Can you test it on
things.
network processors or?
Yeah,
shared?
so I used it on our cluster, and we have InfiniBand interconnect, and it was sending messages across those. So it was, I think, 4 separate processors, and using, I think, 16 nodes on each one. Or 16 CPUs on each one. So this is just kind of outlines how agent requests work. So if you want to go, so this is just a quick demonstration of what happens. So P1, let's say this is the root node, this is the brain. So if you go through, it knows all the ghosts, that's set up at the beginning. So you have your element request, they all know their element request. They send that information to the root node compiles it and makes it this nice big list of, hey, I need to figure out the information on all these guys. He sends out this list to everyone, so they know they have the all request list. So P2 is going to look through this list and he's going to be like, okay, which one of these are mine, which ones do I have to report information back on? They compile that information, goes back to the root node compiles that list, sends it back out to everybody. Everyone updates their ghost processors. So you can see that these all change color because they were all updated. And then they reset their element request list. So when you have agent watches, it goes a little bit faster. So you have your ghost copies, you have your list of people that are being watched. So you know who's being watched. So for P2, you only have P20 is being watched. So you have your agents that you're watching, those are the ones you care about, and then you have your agents watched and changed. So P2 only has this one that's being watched. It hasn't changed, so it doesn't matter. This one has one that's being watched and it has changed, so it's going to be in that list. That information is sent out to the root node. It compiles this information. It sends out a much smaller file than before, or meant a much smaller message than before. And the people receive it, they update their ghosts, and then their list is changed back to 0. So this is the example that James told me to put in. I've never had an analog TV, but apparently when you have an analog TV, it sends complete frames multiple times per second. So it sends out these frames very frequently. When you have a digital
Actually,
TV,
it only sends half of one.
it only sends half of one?
Yes, they're relieved, or they were.
That's what.
There's not a lot of information on them online. I don't know.
Never mind.
That's what VHF is, but you wouldn't know that.
And then there's digital TV where you just update the frames that have changed. So that's why they're able to send it faster and why it works better. So this is some timing results. So with 2 million agents and 20 million agents, so this just shows on 2 processors and 8 processors. Orange is the request and yellow is the watches, just how it speeds up and how we're still able to run it for 20 million agents this was just a basic rumor model that we had programmed in. and you can scale pretty well, more timing results, so simulation execution time, multiple processors, and this is what you were asking about with the probability of having your neighbors on foreign processors. So if you have no neighbors on a foreign processor, it's going to be pretty fast. If all of your neighbors are on foreign processors, you get a really big slowdown, so it's just, it might become more efficient to use. What it definitely is, you should be using fewer processors if you've got that many neighbors on different processors. Alright, so that's all Emmett and I had for content, and we are happy to answer questions and chat with you guys about.
I do have one more comment. If you ever do this, and you want to write simulations for analysis at least that have to be repeatable, knowing how to do a random number generator on multiple processors so you get the same stream, right? So the question is, when I do it in parallel, is it right? The answer, well, right means I get the same answer as if I'd done it on a single processor, right? So I run on a single processor, I get an answer. When I do it on parallel processors, I ought to get the same answer, that I've made it in parallel correctly. And one of the huge problems is to make sure that the random numbers come out properly if you do that. So if you have a simulation that has random numbers, how do you make sure that each guy gets the right one? And we'll leave that for another talk. But I wanted to mention it, that it's very
So now
difficult.
you're going to leave it on a cliffhanger. 'Cause now I want to know how. So do you generate the random numbers using the root, and then you send the random numbers out?
That's one way. There are lots of ways to do it, but what you really need is a random number generator that is somehow tied to the agents themselves, so that I can generate it on my processor for the agents that are on my processor, perhaps. But I might actually have to have a stream for every agent, if the agent can be on any processor. If the agents stay on a processor, then I have a stream for the processor, and they'll be the same. If I go sequentially, I'll still generate all those random number generators and say, if I had put them on 1,000 processors, I would have had 1,000 number generators, so I'm going to make 1,000 even if you're on one. So I get the same numbers every time to do them in the same order. Of course, there's always an issue of how do I break ties, and I have to break them the same way, right? A lot of interesting problems. But you're all clever people, so.
Well, thank you so much.
Yeah, thank
Good.
you.
Any questions?
Can you describe the hardware of your cluster?
So this was the old one, and so it was running. It was like super old. It was from like 2004. I think they initially bought it, and so it was running like I think CentOS 4 or 5.
Well, that's the OS. What's
Okay,
the hardware?
so it had. Oh my, we just bought a new one, and all I do is talk about the new one now. But nothing runs on the new one yet, because all I do is talk about it. So on the old one, I think it had 526 CPUs. Some of them it was a mix of like small and larger nodes. So some of I think like half of the nodes only had like 4 to 16 CPUs, and then the other half had about 32 CPUs. So they were bigger. They were pretty small and RAM. They weren't very big, so it helped a lot to be able to distribute it, just because they couldn't fit that many agents. So just by sheer memory was a big issue. If you want to have the memory for 400, 500 million agents, you can't fit all of that on one node. So it was useful to just distribute. I think the memory for us a lot of time ended up being a bigger issue when it came to agent-based modeling than actually the speed. Because you can kind of wait on something, and I really only scaled up 4 times, but it was just impossible if you can't have enough memory. It's convenient if you can run things faster, but it's impossible if you can't store everything. So
even across the heterogeneous hardware that you had,
yeah.
Did you still have the same amount of memory, shared memory, for a set number of nodes? Like, was it always, 500 meg, 512 meg per 4 nodes, or 4 CPUs or something along those lines?
So
Okay.
I generally, when I did the testing for this one, I just used the nice new nodes that had, the 32 CPUs, just because they were way better to use. And so I used those, and those were heterogeneous, and so they had the same number of memory. If you did have, or they were homogeneous, if you did have heterogeneous, you could decide to split up your agents in a certain way. So, if you've got one with only a little bit of memory, you could distribute it that way.
So this sounds more like a setup that's at the national laboratories, like BlueGNL or something like that, as opposed to, say, a Hadoop type cluster setup.
Yeah. Yes.
Okay.
Mm-hmm.
All right. Thanks.
Yep.
So we have a comment. Oh, I'm sorry. Go ahead. So we have a comment from one of our online streamers, viewers. He said, quote, unquote, I've never had an analog TV. Oh my God, I feel so old. Just felt compelled to share.
Okay.
Well, that's why I brought Christine, because I was in the first computer science class at Indiana University. Before that, there wasn't computer science, so that tells you
Right.
when that was.
When was that?
1972.
Still have punch cards?
I do have a few. I learned how to program the key punch because it was a good way to meet girls.
Really?
26 or
Yes. So if you could do the program card in the key punch, so if somebody comes in and says, I have to write a Fortran program, well, you could set a card in there that would say the first 6 columns are going to be numbers. And anyway, if you could do that, or somebody come in and say, I'm going to use Snowball, and so you'd set up the program card for them, so they had to do less work.
I wonder if that would work today. Hey baby, I know how to do a punch card.
Probably get punched.
Yeah.
Yeah, we should.
26 or 29
Any
punch.
any serious questions about meeting people?
So I would assume there's a sort of some notion of efficiency in how you would partition a problem. So for instance, if you think about the fact that, say, information within certain parts of your simulation really have to talk to each other a lot, and others don't. If you come in from the beginning with a pre-specified partitioning of that may be completely far away from
Yes.
optimality, right?
Some people
do that last.
will actually run the simulation through once with perhaps not a good partitioning to see how they interact, and then from that we'll analyze it and partition it. And somebody said, well, why do you do that? And the answer is, well, if I'm not going to run it more than once, I don't care, right? Might as well run it. If I'm going to run 100,000 copies or 1 million copies, I work on simulations for the FAA, and we have to do millions of copies or millions of runs because they do random, if the airplane does this, and we have to prove that they won't hit each other, or they'll hit each other out of less than 1 out of 10 million times, right, if they
Is
do
that the
this
actual
procedure. So, pardon me?
Is that their actual
Yes.
number that they put?
Yes. So,
So it is
so,
possible.
so in order for them to implement a new procedure, they will run this simulation, and you have to run encounters that look like this, where they do different things in different ways, 10 million times, and show that I don't have more than one collision in the 10 million.
But are there principled ways of thinking about this partitioning? And I mean,
Absolutely.
it's sort of a spectral partitioning, notions of that
Sure.
sort, right?
And that's, you talk to the domain expert that says they can explain the problem, then you need the parallel computer guy to say how they ought to partition it to do it. Another issue is often that in a high-performance computer, they have less memory per node than what you normally have like on a laptop.
You have to keep it flexible the whole time. So you have to go in, you can't parallelize it too early. You can't think about a partition when you start to write it. You have to write it real small, make sure it works, and test it out a little bit, and then think of a partition. With heat diffusion or with fluid flow, it makes sense to go this way instead of this way, and there's different ways you sort it out. So doing the domain expert and then working with someone that has a background in parallel computing. Normally you can get by like just yourself if it's a smaller scale project, but if it does go up and you're gonna,
I would encourage you to look at the literature, and see what people have done. But there are different methods. For instance, there's something called particle and cell, where I'm interested in particular in certain particles that go through this space, but there's magnetic fields or whatever. And so I might be able to generalize the cell itself and the boundaries I worry about, and I only have to map the particles as it's going through that cell at detail, and so I don't have to move as much state, because while this particle's going through my cell, the edges don't change much. Anyway, look at the literature for your kind of problem and see what people have done, and then be clever and do something else.
Yeah.
So bottom line is that it is a practice in a sense. It's not.
Yeah.
It's an art.
It's not just.
And just build it as flexible as possible too, because it's really easy to code something that'll work on 2 processors. It's really hard to code something that works on N processors.
This is a problem that will not parallelize, right? Anybody, right? Because the ordering is random for each of the agents, And the model only works if you do it in random, and so it does me no good to parallelize it, cause I have to do them one at a time.
Is that what he's talking about, just load balancing?
Yeah.
Partially, yeah.
Yeah.
And load
Yeah.
balancing is often done dynamically. You don't
That could be
set
too.
it ahead of time, you don't
Yeah.
ask a domain expert, you let that emerge from the
Yeah.
system and let the system balance itself.
What you make
Yeah,
sure of
we have
is that
provision
your
for moving
boundaries
things.
don't have a
Random question. Are there courses that made to teach this type of stuff?
Yeah, so
Oh, I see. So
there's a
actually
CSI
choosing
class on
boundaries.
parallel
That's right.
computing, I think.
Okay, so
Uh,
that can be
But of course,
Dr.
here's
Weiler?
a problem. If you
I
end
took
up
it
with
with,
something that's very
Richard Mulner.
homogeneous in
Okay.
sizes, right, so you end up still with
Yeah, yeah.
a system
I
that
took it
has
with him.
problems
No,
because
no.
of
Yeah.
very little communication.
Good to know, good to know. Thanks, man.
Oh, I see, yeah, so that's not easy.
There you are, thank you.
But it's a really good class too. It is,
Yeah, because
I'll
you-
edit that
the
part.
programming is
yeah,
hard,
you have to know something
cause the
about
coding, he does do the coding has to be in like C or Fortran.
Yeah.
So, the parallel computing class, does Lunar still teach that?
I don't know, maybe. No,
Okay.
probably not, really, no.
Okay, is it still being taught in CSI or did it move to,
I doubt it.
okay.
Yeah, I'm very much down.
It's a good class though, you do have to have a bit of programming background.
Well, thank you so much. You can stay around for a little bit
Okay.
if you have questions.
All right.
If you could, and thank you very much.
Okay, thank you.
Thank you to our online viewers.
Answer all questions for the online viewers.
I did have a terminology question.
Excellent, by the way.
Oh, cool, yeah.
All of it. I looked at it. You made it sound simple.
Hopefully that's,
I mean, it's not
yeah.
simple. And that's like the most clear I've ever had it. I've never bothered with this stuff because I have too much information in my
I've
mind.
Yeah.
heard,
But actually
but I
seeing you
haven't.
guys doing it, well,
Well,
and that's the problem.
Uh,
And that's the problem. That's why you're going to be talking about it.
You know,
So we
all I
have to
use
do
is
it.